Hi, so welcome back. So in this lecture, we will go over the summary of the various concepts that we have learned in the last couple of lectures. So we had random variables, we had probability mass functions or PMFs for discrete random variables, we had PDFs or probability density functions for continuous random variables, and we had CDFs, which were cumulative distribution functions for both. And we will also learn a few more properties connected to all of these. Coming to x, which is a random variable, so we said that x was a random variable, was really a function from the sample space to real numbers. So the sample space was the set of all outcomes for an experiment. So for example, if you rolled a die, it would be 1, 2, 3, 4, 5, 6, all put together in a set. If you tossed a coin, you could have heads and tails. That would be the set of all outcomes. That would be the sample space. So basically the function of a random variable was to assign numbers to the outcomes in the sample space. So sort of code them numerically. Okay, for an experiment, you could have very abstract or non-mathematical objects. For example, heads and tails, they are not mathematical objects. If you walked into a jungle and somebody asked you what's the probability of spotting an elephant, well, the elephant is not a mathematical object, but it helps to code them with numbers. Okay, for example, in one of the examples that we have done in the previous couple of lectures was that we had a box and we had a few balls in them. Okay, 9 of them in fact. 3 were red, 4 were white, and 2 were black. And we coded them with numbers. For example, we coded the red balls with 1, we coded the white balls as 2, and we coded the black balls with 3. So instead of calling them red, white, and black, we could just call them by numbers now. Okay, so really that's the work, that's the function of a random variable, is to assign numbers to objects which are outcomes, and then we can talk in terms of numbers because of course we're doing mathematics. So coming to what is a discrete random variable. So now let's come to the summary. We have sort of few differences between a continuous random variable and a discrete random variable, and a few similarities as well. So first of all, x would be called a discrete random variable if the spectrum of x, which is the image set of x as a function, if that is countable. For example, in the example of this box containing 9 balls, the image set was 1, 2, and 3. 1 for the red balls, 2 for the white balls, and 3 for the black balls. So the image set really is a countable set. You can count 1, 2, and 3, which is a subset of the real numbers. So because that was countable, the random variable which was assigning the numbers, that was called a discrete random variable. Well, in case that spectrum or the image set is not a countable set, then x would be called a continuous random variable. Well, we will come to this definition of continuity for a random variable is a slightly twisted one, a slightly reversed one. But for the moment, if x is continuous, then the spectrum of x could not be countable. Okay, because if it was countable, it would be called discrete. Well, one of the examples that we did was picking numbers in the closed interval 5 to 7. Okay, so there were infinite number of numbers between 5 and 7, including 5 and 7. And so, because x was really picking numbers from there, so the image set, so we in that example, x, the random variable, was really the identity function because the sample space had numbers. So they had numbers between 5 and 7. Which we had to pick. And so we kept the random variable as identity because we were already dealing with a sample space which had numbers and we had no reason to change them to something else. If we had heads and tails, we had reason to assign numbers to them. We already had numbers from 5 to 7, so we kept the image set exactly like the sample space. And so the spectrum of x in that case was 5 to 7, all numbers between 5 and 7, including 5 and 7. So that's not a countable set. In fact, it's an uncountable set. There is a slight difference, but anyway. So in that case, x turned out to be a continuous random variable. And we can, the examples I'm talking about, we talked about them in the previous lectures, so you can refer to them. So now coming to a few more points, the cumulative distribution function, CDF, it was defined exactly the same way for both the cases. Capital F, which is how it is written normally, CDF is defined from real numbers to this closed interval 0, 1, because it's defined in terms of probability, so it has to be, the values will have to be between 0 and 1, okay, including 0 and 1. So it's defined as the probability that the discrete random variable, which is x would take values smaller than or equal to small x. Okay, so what is that probability? You calculate that, and that would be the value of capital Fx. Exactly the same way for continuous random variable. There is no change there. For now comes the concept of a PMF, or the probability mass function, which is slightly different from the probability density function, and they're also kind of defined differently for the two cases. The 2 points are quite different in that sense. So for PMF, it's written as small f, which is defined from the spectrum of x. For example, 1, 2, 3. For the example of the boxes and the balls, and the PMF at a point in the spectrum which I can call xi, because this set is a countable set. I can number them. I can list that set, the elements of that set, as x1, x2, x3. So the small f, or the PMF at any point xi in the spectrum, is given by the probability that the value assigned is xi. Okay, that was this definition. Okay, what's the probability that, for example, if x in the example x equals 1 was one of the outcomes. It was the code for the red balls. So probability x equals 1 would mean, what is the probability that you would pick a red ball? Okay, x equal 1 means which outcomes which were coded as 1. Okay, so and that probability, whatever that value is defined as the probability mass function at the spectral value 1. Okay, so f of 2, for example, would mean what's the probability that you would pick a white ball, because x equals 2 meant the event that you picked a white ball. Okay, but for continuous random variables, this PMF gets, the name is not kept the same. It's called the probability density function, because it kind of serves a different purpose. Well, not a different purpose, but kind of defined differently here. So it's a function. So we've changed the domain as well. This is a function from the spectrum, but this is a function from the real numbers to 0, 1, closed interval 0, 1. But it is that function which sort of on integration from minus infinity to x gives you the CDF. So once you have defined the random variable, you already know the CDF, because you defined it in terms of the random variable. So then for PDF, you have to basically look for a function which matches or which satisfies this equation for all x. Okay, if you can find if you can find a function small f which satisfies this equation, that capital Fx would be the integration of this new function from minus infinity to x, then this new function would be called the PDF. And we found it the last time in the example that we were picking numbers between 5 and 7, closed interval 5 and 7. We found out that in that interval from 5 to 7, this function turned out to be a constant function, which was half, which is really the case of uniform distribution. And we will come to, it's a particular kind of distribution. We will come to that. We did not name the distribution then, but that was the example. So yes, so for continuous random variable, you're supposed to find a function like this which satisfies how capital F, or the CDF, is defined. Okay, so the two are defined differently. This is defined directly in terms of probability. This is defined in terms of the CDF. Okay, once you define the CDF in terms of probability. Okay, right. Coming to the fourth point, it shows that there's a difference, but yet there's a lot of similarity here. So if you are going to calculate the value of CDF at a point x, okay, x, remember, can be any real number, because the CDF is defined on all real numbers. So if you're going to calculate the value of f at the CDF at a point X, it basically meant that you sum up all the PMFs at the spectral points, xi's are spectral points, but those xi's will have to be less than equal to small x, this point where you're calculating the CDF, the value of the CDF. Here, in spirit, the concept remains the same, but except that because we're not dealing with a countable set, we're not dealing with listed numbers like x1, x2, x3, but dealing with more like a continuous set, for example, 5 to 7, this summation gets changed into an integration, and an integration where the PMF and the PDF on this case serve the same purpose. This is the integration is really a continuous sum. Okay. So here we are summing over the PMF, here we are summing over the PDF, but it's a continuous sum. And again, you see, we take spectral points up to x, and there is no limit on where we can go on the, below x. You can go up to minus infinity if you had spectral points up till there. Here also, it's the same. We go up to the upper limit x. This is where where we're trying to find it, the CDF, and there is no bound on the lower limit. Okay, you can go up to minus infinity. So that's we have derived both of them. Then this was capital F, or the CDF expressed in terms of PMF and CDF expressed in terms of PDF. Well, you can express PMF in terms of CDF and similarly PDF in terms of CDF. Okay. So the roles are reversed here. So we found last time that because this function, the CDF in this case was an increasing step function. If you remember the graph that we had drawn the last time, it would go straight, it would go, in a straight line along, and then finally when it hits a spectral point, there is a jump. Then again it goes straight, goes flat, hits a spectral point on the x-axis, takes a jump. Okay, it's a step function, which is an increasing step function. So there were discontinuities at the spectral points, and this was the amount of discontinuity. Okay, so the function was really left discontinuous. Once you went from the left to right, you had to take jumps. Okay, at the spectral point. So the function capital F it's an increasing step function with discontinuities from the left. Okay, left discontinuous. There was no discontinuity from the right, because if you came to a spectral point from the right, you would hit the value of the spectral point itself. So there was no problem there. So what we found that at spectral points, the value of PMF was really given by the jump, or the amount of discontinuity, which of course is defined in terms of limits, and we found that the last time that it was the CDF calculated, the right hand limit of CDF calculated at the spectral point minus the left hand limit of CDF calculated at the spectral point. So you come from, if this is a spectral point, you come to the spectral point from the right and from the left, you will find the difference. Okay, that's the amount of jump in the step. Okay, right. And for this one, we found through a bit of an analysis using Taylor's theorem, and we found that the PDF can be expressed in terms of CDF by just differentiating at whatever value you want to find this PDF. Remember, this PDF can be found on any number R, because it's defined on real numbers. So that's a slight difference there. Okay, and of course, in this case, capital F turned out to be a continuous increasing function. So for the example that we took the last time, where we were picking numbers in the closed interval 5 to 7, the graph of F it went on like this. Then there was a slant, there was a sloped line which was increasing, and then finally once it hit 1, it stayed the same again. Okay, so that was the graph of F. Okay, so it was kind of like this. So it was an increasing function but continuous. So in this case, it was like that, and all of these were spectral points: x1, x2, x3 like that, okay? And here in that example, it was 5 to 7, okay? So this was the graph. So left discontinuous, but no, there is no discontinuity here, but it's increasing. Well, there was some similarities as well. We found from the graph itself that if you went to minus infinity, the value of capital F would turn out to be 0. You can see that it's falling on the left, and it goes to 0 as you go towards minus infinity, and it stays at 1 once you, so after the last point it stays at 1, okay? And so the value of capital F would be 1 at infinity, similarly for this one, okay? That's just evident from the graph itself. Well, there is one point which we hadn't discussed the last time, and it's a very important point, and it'll come out to be one of the properties, and then we will show this now. So if you had a spectral point, if you take a spectral point for a discrete random variable, of course, the probability that the value of an outcome is xi, that's, for example, the value of a ball is 1, that is red ball, is equal to how it's defined in terms of, PMF. Obviously, PMF is defined like this. But this may not be 0. For example, the probability that you pick a red ball, that is probability x equals 1, was 3 out of 9. Okay, in that example, probability x equals 1 was 3 out of 9. So please refer to the example we had done the last time. This is not 0 because, there were 3 balls out of 9 choices. However, for a continuous random variable, if you are going to find the probability that x equals some spectral point, x, small x, then that probability is always going to be 0. It's a huge difference, okay? So probability x equals some spectral point may not be 0 for a discrete random variable, but probability x equals some spectral point is always 0 for a continuous random variable, okay? So that's one big point of difference here, okay? Let me star mark that point, and we will discuss this now, okay? It will come under one of the properties that we will discuss today, okay? All right, so let's take that up. So let's discuss how that happens. But before that, leading up to it, we have to do something more. So first of all, suppose I want to find the probability. Suppose you have 2 numbers, okay? You take 2 numbers, real numbers, A and B, and suppose you take A to be less than B. Okay, what happens now is that suppose I asked you to find the probability that x is greater than small a but less than equal to small b. I want to find this probability, okay? Well, I want to find a useful formula for this probability, okay? And what we see here is that if you have, so this is going to be, I'm just going to write I'm going to write the formula first and then tell you how it comes. So this is actually going to be probability x less than equal to b minus probability x less than equal to a. This is what it is going to be. Let's see how, okay? This is a useful formula, okay? And why is this useful? Because this really is the CDF at B. You see, that's the definition. What's the CDF at B? It's the probability that the random variable takes values less than equal to B. And similarly, this is f of A. Okay, so for a given problem, if you know the CDF, if you know the cumulative distribution function, and if you have to find a probability that x, the random variable, takes values between two numbers, endpoints here, then that probability would just be given, you just have to calculate the CDF at the 2 points and you would have the answer. So it's a useful formula here, okay? So let's see how, so the important thing is how do you get this step from this one, okay? So the way we can write it, because B is the bigger number here, let's say I look at the event that X is less than equal to B, okay? This can actually be written as, so if X is to take a number less than equal to B, either it can take numbers less than equal to A, which is smaller than B, or it would take number which is greater than A but less than equal to B. Of course, it has to be less than equal to B, whatever number X takes. But either it's smaller than A or it is in between A and B. Okay, so we are breaking up an interval like this. Okay, so if this is A and this is B, this is B. So any number left of B, less than equal to B, can either be, for example, it can be here. In that case, it is less than equal to A. Or it can be here, that even then it's less than B. But then it's not in this interval. It's in this interval A to B. Okay, so that's the way you can break it up. But now I'm looking, so if I look for the probability that X would take a value less than equal to B, this would be the probability of this event. But of course, these two are disjoint events, because either X can take a value which is less than A, or it can take a value which is greater than A, less than equal to A, or a value which is greater than A. It can't take both, okay? So I hope that much is clear, okay? The values assigned can either fall below A or equal to A, less than equal to A, or the value will be more than A, but less than equal to B, because it has to be less than equal to B. So because these two are disjoint, I can actually, what I can do is, by using the axiom, one of the axioms of probability, I can find the individual probabilities and I can add them up. That was the axiom, because you had disjoint events and the probability of the union could be broken up as a sum of the individual events, okay, probability of the events. And so now if I take this to the left hand side, I'm left with this on the right hand side, and so you have probability A less than X less than equal to B. You just take it to the left and you have this, okay? So I don't have to write it. So this is what it is. If you take this to the left, the probability X less than equal to B will be probability X less than equal to B minus probability X less than equal to A, and you have the result. Okay, so it's just a very small calculation. Okay, right. So once we establish this, we know that this is written like this because that's the definition of capital F. Okay, so this is an important. You can think of it as an important formula. Okay, let's just tick mark that just to tell you that it's a useful formula. But we can do a little bit more here. This, if you're dealing with a discrete random variable, so suppose X is discrete, okay, then in that case, this is given by, you remember the formula, that this is given by the PMFs of various spectral points, but these spectral points would have to be less than equal to B. I'm not writing xi belongs to spec X because you all know that these will be spectral points. So this is the summation in terms of the PMF at spectral points where these spectral points will be less than equal to B by formula. And similarly, this is going to be the summation of the PMFs at spectral points where the xi's are less than equal to A. So this really is going to be a summation of spectral points where the spectral points are greater than A but less than equal to B. I hope that much is clear, because you're adding the spectral points which are all less than equal to B, and then you're subtracting all the spectral, you're subtracting the PMF of the spectral points for the spectral points which are less than or equal to A, so you're left with only those spectral points which are between A and B. Okay? So this is the bigger sum. You're taking away a part of it by subtracting this, and so you're left with a smaller sum, where this summation will now be on spectral points which are left between A and less than or equal to B. Okay? So, and this will be a strictly greater than A because you're taking away up to A, including A here. Okay? So this is the formula. So let's just write that down. And this is when X was discrete. Okay? So probability that A is less than capital X is less than or equal to B, this is given by this thing. Summation of over all spectral points which are greater than A but less than or equal to B. This is when X is discrete. Again, a very useful formula, because if you're given the PMF of a particular problem and you have to calculate this kind of a probability, you just add the PMF at various spectral points ranging over this interval here. Okay. Now, okay, what happens if X is discrete? X is continuous. So this is when X is discrete. What happens when X is continuous? Capital X is continuous. What would that be? So let's rub this out because we've already written out the result. If X is continuous, then this formula is no more in terms of summation, but in terms of an integration from -infinity up to where we are calculating the CDF of the PDF, the probability density function, because now we have X is continuous. We're dealing with X continuous now. So ft dt, this is an integration, but you're taking away another integration up to A, which is smaller than B. So you're left with integration from A to B, ft dt. It's the same logic as the sum. You're summing, it's a continuous sum, its integration is a continuous sum. You're summing from -infinity to B, and then you're taking away the sum from -infinity to A, so you're left with the sum from A to B. Okay? So this will be, the same thing will be, now in terms of integration from A to B, same, this is exactly same analogy here. The sum between A and B, continuous sum between A and B, of the PDF now, ft dt. This is the case when X is continuous. Okay, so this is, let me just box this. It's an important result. Okay, in fact, this can go down as a point, as a 9th point in that chart of similarities and differences. So this would be a difference, but still similar. This quantity is given in terms of a summation like this. This quantity is given in terms of an integration like this, ranging over whatever range we're looking at for the random variable. Okay? Right. Now, coming to this problem of finding. So let's just rub this out. I'm going to keep this formula here for the moment. Now coming to the point number 8, where we said that if X is a continuous random variable, in that case we said that probability that X is equal to some spectral point, okay, would always be 0, where small x is a spectral point. Okay, this is what we will prove. Okay, well, what we can do is, instead of taking it exactly equal to X, let's just make use of this formula. I'm going to look at, this is what I'm going to look at eventually, but right now I'm going to just say that I'm just going to look at X, which lies in a very small interval from X. Okay, so I'm basically taking this X to be A and B to be X with a small increment delta X. Okay, so I'm looking for this probability here. Okay, And I know that to find this probability, what I can do is if I take this displacement, this small delta x, if I can take the increment as small as possible, then x becomes almost equal to small x. So basically what I'm doing is I'm looking for limit that delta x goes to 0. As delta x, or the interval, goes to 0, I'm getting this result, okay, probability that x is equal. So here it is. So this is x plus delta x. I'm looking for the probability that capital X would take a value here. If I push this to the right, to the left, if I take this difference here, of course, is delta x. The smaller I make this delta x, the more towards x I reach, and I'm basically pushing the value of capital X more towards x, and finally we have this. Okay, so for this I can use this formula because I know that x is continuous. So this is just going to be an integration from x up to x plus delta x, okay, for a and b, and we have the PDF ft dt. But of course, because this delta x is very, very small, okay, it's very small, this is almost going to be equal to, again, this is from Taylor's theorem really, but it's going to be almost equal to, up to the first order, fx delta x. This is like Riemann integration, okay? You approximate this integration by the value of f at the point and that small distance over which you're integrating, okay? And since so really I have to put that limit, that's what I'm taking. Here also, limit delta x goes to 0. As delta x goes to 0, this is a proper number, okay? It's a constant number because x here is a constant, it's a spectral point. As you take delta x to 0, this whole thing becomes 0. And so finally, what you see is that by this little argument where we went through limits, we found that the probability that x, the random variable, would take a value which is from the spectral point is actually 0. So coming back to the example where we were picking numbers between 5 and 7, initially we asked a very important question: is what is the probability of picking the number 5.9 from this interval? What was the probability of picking 5.9? And since 5.9 is a spectral point and it's just one point like x, so therefore the probability that you could pick 5.9 from this would be 0. So that answers the question that we had asked initially. So we asked two questions. Please refer back to the video the last time. We asked two questions. One was, what would be this probability? And then we could not answer it at that point, so we changed the question a little bit. And so here it is. Here is the answer, finally. With all the properties put together, we can say that the probability that you would pick the number 5.9 out of all these possible choices is actually going to be 0, because you can at least have a logical... That's what our intuition would also tell us, because just one number out of so many possible numbers, the probability that you would pick exactly 5.9 is really 0, okay? So, right, that actually explains this. So, one last thing that I want to do before we wrap off this lecture is just going to be this. So if somebody, in the case when x is continuous, that's the case when the probability that x is equal to some spectral point, that contribution is 0, okay? This is a very special point, okay? In this case, the question is, if I ask you to find the probability that x is between a and b, but including a and b, that really would be the same as probability x less than a less than equal to b. In other words, you can omit the point where x you can omit the case where x takes the value a. Okay, the probabilities would really be the same. Okay, it doesn't matter whether in this range of you're looking for an event where x takes values between a and b, and in this range you have included a. But if you exclude the range and then ask the same question, the probabilities would be the same. Okay, this really follows from an argument which we have already covered. So this event that x is between a and b, including a and b, this event can be broken up as either x is equal to a, or that x is greater than a but less than equal to b. It's like what we did before when we were proving the result that x between a and b was equal to fb minus fa. So it's the same argument. So if you're picking, if you're looking for the event that x takes a value between a and b, either it's exactly a, which is this, or it's more than a but less than b, less than equal to b. So if you're looking for this probability, that's what we're looking for, you would take the probability of this thing. And again, by the same logic, because these are disjoint events, you can break them up by the axiom. This is going to be probability x equals a plus probability a less than x less than equal to b. But since the contribution from x equals a is 0, if a is a spectral point, of course we are dealing with spectral points here, the probability that x equals a is 0, but when x is continuous, we're dealing with a continuous random variable. So it's just going to be probability a less than x less than equal to b. And so we have the result. So really what it tells us is that you can freely, this would also be equal to a less than x less than b. You can freely add or remove endpoints without changing the outcome without changing the probability. Okay, so this is the same as probability a less than equal to x but less than b. So all the possible points, here both the endpoints are included. Here only one of them is included. So these two, both are omitted, but they will all have the same probability, because really the contribution for probability from the endpoints is 0. Okay, so that's another important result which we have to keep in mind. Okay, and this is not the case when x is discrete, because probability x equals small x may not be 0. Okay, so please keep these are a few additions to the list of similarities and differences. Okay, all right, so I think we will finish this here, take things forward in the next lecture. Thank you.